Polarity, it's directly related to the shape of the molecule. It determines many of the properties of the substances. So what is polarity? We've talked about it with our bonds. We looked at polarity of bonds. So what in general, guys, is polarity? If something is polar, what's happening? Got to know this term for the vocab quiz tomorrow. What's happening when something is polar? It's cold? No, it's not cold. Look back in your notes. Polar. We talked about polar bonds and non-polar bonds.
It's a shared pair of electrons that is held more closely by one of the...
Yeah. If something's polar, okay, we can simplify that. Polar, guys, means unequal. Unequal sharing going on. Now, we've talked about it in terms of a single bond. Okay, a single bond. Now we're going to apply that same concept to a molecule. So if something is polar in terms of its molecular shape, one part of the molecule is going to have more electrons. So it creates that negative, that slightly negative charge. And the other side would be slightly positive charge. That's where we get those intermolecular forces that we'll talk about later on in the year. So something that's nonpolar then would be what? What does nonpolar equal? Equal sharing. Good. Again, we've looked at it in terms of bonds. As a review from last week, when you figure out bonds, if they're polar or nonpolar, you look at their difference in electronegativity values. So something like NH3, we would look at its bond. We'd say, oh, what's the electronegativity of nitrogen and hydrogen? And then you'd subtract those out. And then you look at just one single bond, because all of those bonds would be it. Now we're going to apply it to a molecule as a whole, a complete structure. So knowing the shapes, guys, you got to know those VSEPR geometries that we talked about yesterday. We're looking at symmetry. Symmetry within the molecule is going to dictate if it is polar or nonpolar. If the molecule has a symmetrical shape, what does it mean to be symmetrical? Yeah, it's the same. So if you were to draw a line down the middle of something, if I drew a line right here, all right, the line of symmetry would be right about there, where on each side of either of those lines, either red or blue, they're going to be the same on both sides. Okay? So we're going to look at the molecules to see if it is. Basically, the idea is that they cancel each other out. Those satellite atoms are the same. They're going to cancel each other out. If it's symmetrical, it's usually nonpolar. Not always, but usually. And it's not just one line of symmetry, it's got to be multiple lines. So it's got to be X, like if you're looking at it in terms of the X-axis, it's going to be symmetrical as well as the Y-axis. If it's non-symmetrical, that means they do not cancel and it's going to be polar. So if it's non-symmetrical, guys, it's going to be polar. Typically, VSEPR shapes, VSEPR geometries that are typically nonpolar include linear, trigonoplanar, and tetrahedral. Notice what I have down here. If it's not in your notes, I highly recommend adding it. Otherwise, if it's there, circle it, highlight it, something so that you know. If the surrounding atoms match, then they're going to be nonpolar. If they don't match, then it's polar. Okay? Think about it like you're playing tug of war. All the elements are trying to fight and pull those electrons from the central atom. If they're all the same, they have the same strength, so they're going to be pulling at the same rate. Okay? They have the same strength to pull on those electrons. If you change one up, that's going to be somebody who's bigger or smaller. That's when you've got a sort of a winning tug of war going on. So think about it like this. If you play tug of war against yourself, you're not going to win. Right? You're going to be pulling with the same amount of strength on both ends of that rope. But then if you I'm trying to think of it. You take like a 2-year-old versus like a 25-year-old, who's going to win that tug of war? The 2-year-old, right? I mean, absolutely.
What 25-year-old is going to be that mean to what you?
That's true. That's a good point. Either way, one's going to win and one's going to lose. You get the idea. You can think about it. I mean, let's be honest. Would you, if you're going against a 2-year-old, and it was a prize was on the line?
I'm not that much of a...
You're going to let what if it's $1 million? That's exactly. All right, there's the analogy that we're going for. You're just, dragging it away. All right, you get the idea, though, guys. Okay, we're going to do some practice here. You'll see what I mean. But typically, these are the 3 shapes of our 6 that are going to be symmetrical. But again, surrounding atoms need to match. Okay, they need to match. If they don't match, then there's going to be an unequal sharing taking place in one of the directions, and you're going to have a polar molecule. Now, is this always the case? No, there's going to be some exceptions to the rule. We're going to try to cover the most general pieces. We're not worried about all the exceptions that are taking place. Asymmetrical, meaning non-symmetrical, it's always, always, always polar. So both bents are always polar, and trigonal pyramidal is always polar. Surrounding atoms, guys, even if they don't match, what do these three structures have that the first three don't have? There's something big here. Okay, this is something we're going to add to our notes. What do both bent structures and trigonal pyramidal have that linear, trigonal planar, and tetrahedral don't have? Big concept question right here. Lone pairs. Okay? These three here that are asymmetrical always, they have lone pairs. So when you have lone pairs in a structure, guys, already that's going to make it polar. Think about it. It's valence shell electron pair repulsion. Those lone pairs of electrons, guys, they dictate the shapes. They push everything else away, making things polar. Remember, what type of charge do you have in lone pairs of electrons? What's their charge? What's the charge on an electron? Negative, okay? So you've got all this concentrated area of negative charges. That's going to make a overall polar molecule where it's slightly negative at one end, and the other side is going to be more positive, okay? So, however you need to remember this, look at the symmetry when you draw them out. This is where also, if you draw water like this, you might think, oh, that's symmetrical. If I drew a line down the middle, that's the same on both sides. If I drew a line this way, it's the same on both sides. That looks like a non-polar molecule when you draw it like this. But those lone pairs, remember, force these hydrogens to go away from the other lone pairs. Is that symmetrical now?
No.
Absolutely not. Is it symmetrical? If it's symmetrical, it's got to be symmetrical every way you look at it. So we could draw a line there. There's that line of symmetry, but it's not as simple. Remember, these are two-dimensional images that we're drawing, but it's really three-dimensional. Is that what it's called? Is that the mathematical term, radial symmetry? Sure. All right. I want you guys to draw these three structures in your notes. Okay? Determine the VSEPR geometry, and then we'll talk about polarity. So when you draw your Lewis dot diagrams, your Lewis structures for these molecules, folks, this is what they should look like. Any questions? What is the molecular geometry for water?
Polar.
Geometry.
Oh.
Bent. Okay, so we have a bent molecule here. Carbon dioxide is? Geometry, guys. Linear. HCN is linear as well. Okay? Now, draw a line. And again, it's in more than one direction. So if you have even one axis that is not symmetrical, it's going to be asymmetrical. Meaning it's what? If it's asymmetrical, it is polar. If it's symmetrical, it is nonpolar. So for water, I'm going to start with my y direction. Is that symmetrical? No, right away, guys, if you have one axis, just start with your x and y axes, like draw those over it. If it's not symmetrical, you know it's going to be polar. So this is a polar molecule. Right? Even if we go that way, it's the same idea. Carbon dioxide, let's take a look here. Is that symmetrical? Absolutely. Is this symmetrical? There you go. So this is what? Nonpolar. Think about it. This is a good example to look at. Okay, good example to look at. So, over here you've got on one side, okay, you've got oxygen and oxygen. So it's the same element on both sides. If we switch that up and said sulfur instead of one oxygen and one sulfur, that's not going to be symmetrical anymore. All right? So it's that unequal pull. So last one here, HCN. If we do it this way, well, that's a bad line, but that's symmetrical, right? But you got to check more than one. You got to check both X and Y. All right, there you go. It is asymmetrical, so it's going to be polar. And guys, just take a look at it. Nitrogen, look where all the electrons are. There are way more electrons on this side than there are over here. This is going to be your slightly negative part, and this is going to be your slightly positive. Okay, remember, chemists bond, those three elements, they've got the highest electronegativity. They want the electrons the most. They're going to be the bullies, and they're going to pull in the electrons as much as they can. They want to take those in.
So in order for it to be symmetrical, does it have to have like the same element on either side?
That's a good rule of thumb right there, okay? Is yes, it's going to have the same element on both sides. Now, we can take it a step further, and we can look at their electronegativity values. If they have the same electronegativity value, they're going to pull on that central molecule the same. I want to say nitrogen and chlorine have the same values. We're keeping it simple right here. I don't anticipate you seeing anything where it would be, like something, I don't even know if this would be a good structure, probably not. Okay, where you had like Cl over here and you had nitrogen over here. It wouldn't happen. Okay, but just for an example, I believe they have the same electronegativity values. You guys could look those up. They would pull the same because they have the same value. You're not going to see anything because you're not going to have a molecule that could exist like that. All right, so it's going to be obvious. All right. Any questions? I want you guys to go back through all of those 1 through 14 that we've done the past 2 nights. You guys have drawn their structures. You have identified their molecular geometries. Now I want you guys to determine polarity. All right, here we go. Tellurium chloride, guys, number 1. Is that polar or nonpolar? Is it symmetrical or unsymmetrical? It's polar, right? Take a look right there. 1 line's all you got to draw. It's not symmetrical. Number 2. Now this one has resonance going on. Resonance structures, guys, if you take a look, you've got oxygen pulling equally. So this is going to be what? Nonpolar. Okay, nonpolar. It's easier to see this when we draw it with the dotted lines, the shortcut method like this. When you draw it out, each one, but remember that double bond is constantly rotating to be in the lowest energy state possible for the molecule. So we're going to consider that to be nonpolar. PO4 minus phosphate, that's going to be nonpolar. I2 is going to be nonpolar. You've only got the element, guys. It's like playing tug of war with yourself. It's going to be symmetrical. ICl, though, is going to be polar. You've got different elements there. H2S is polar. All right, I'm going to go back to the other ones. Give me a second. All right, I'm going to use a different color here since I've already used. I've already used blue, so I'm going to use something different. All right, NO2. NO2, it's a bent geometry. Is that going to be polar or nonpolar? Polar. Anytime you've got a lone pair of electrons on that central atom, guys, it's going to be polar. Okay? Trigonal planar here, number 8, carbonate. That's going to be nonpolar. Good. Water is polar. P2 is going to be nonpolar. PCl3 is going to be polar. It's got that lone pair of electrons. SF2 is polar. BRCl is really? Take a look, guys, right there. Is that symmetrical? It's polar. You've got 2 different elements there. So it's like you playing tug of war with that 2-year-old. You're going to win. Okay? If we take the emotions out of it, you're going to win. Just go based on strength. And the last one, tetrahedral. Remember, tetrahedral is usually nonpolar. Do you have the same elements all around it? Absolutely. So that's going to be nonpolar, equal sharing. Any questions?